Okay, so the main question of the mini course is the following. So, given two right-angle arcing groups, right, or RAAGs for short, how to determine whether one is isomorphic to a subgroup of the other. Okay. So in other words, what we want to understand is the embedding problem between some focusing on some specific class of groups. So right-angle arcing groups, I will define them in a moment. But given a specific family of groups, these are some basic questions we can ask to test whether or not we understand this family of groups. For instance, how do we know whether the group is finite, trivial, infinite, abelian? I don't know. The isomorphism problem, we would like to be able to distinguish two groups in this family. For right-angle arcing groups, many of the basic questions are really well understood, but the embedding problem is one of the few where the problem is still widely open. And so in this mini course, the goal will be to describe some geometric framework to find at least some positive answers to this question. So the plan is the following. So the first lecture today is a crash course on RAAGs. Okay, the second lecture is a crash course. Sorry, there is a missing word. On a quasi-median graph. Quasi-median graphs. So it's a geometry which will be useful to study this question. And in lecture number 3, it will be, well, putting everything together. So how we can use this geometry to construct some really non-trivial embeddings between right-angle arcing groups. So non-trivial embeddings. And finally, in lecture 4, I will describe in some specific case an algorithmic solution to this problem. So an algorithm in dimension 2. Okay. So in full generality, we basically don't know how to solve the problem, but if we restrict ourselves in some subclass of right-angle arcing groups, it is actually possible to solve the problem thanks to an algorithm. Okay. Okay. So for today, we focus on what are right-angle arcing groups. So let's begin with the definition. So fixed gamma graph. And you define the right-angle arcing groups by the following presentation. So the generators are the vertices of the graph, and the relations are just commutators given by adjacent vertices. So here, V gamma is the vertex set. Of the graph, and E gamma is the edge set. Okay. So sometimes, so this is the definition of RAAG. Sometimes it is also called a partially commutative group, which is maybe a more descriptive terminology. And there are two extreme situations So the first case is where gamma has no edges, and in this case you have no relation, and so what you get is just a free group, right? So if you have no edges, then A gamma is free. Right? And in the opposite direction, if gamma is complete, then, sorry, if gamma is complete, then A gamma is free abelian. Okay? So the picture to keep in mind is that if there is no commutation, you have a free group. If you have the commutation as much as possible, it's a free abelian group, and everything in between is the family of right-angle arching groups. So usually one says that right-angle arching groups define an interpolation between free groups, non-abelian free groups, and free abelian groups. Okay? So we can put some explicit examples. For instance, if I take a path of length 2, in this case I have one generator which commutes with two generators, and these two generators do not commute. It's isomorphic to a free group of rank 2 times z. Okay, so you have this factor comes from this generator, and these two generators generate this free. Another example is, for instance, this one. You take 4 cycle, then it's isomorphic to a product of two free groups. Okay, because you have these two generators, they generate a free group. These two, same thing, and the two actually commutes between, because these generators, it commutes with this one, and these generators commute with this one and this one. And then, okay. Okay, so one of the first problems we can ask about right-angle arching groups is a word problem. Okay, so every element G inside my RAAG A gamma can be represented by a word. Say W, so written over V gamma union V gamma minus 1. So just a word of generators. Okay, and the question is, okay, I have some specific word of generators. How can I decide whether or not it represents the trivial element? Okay, that's the basic question. And the first observation is that there are a couple of simple elementary transformations we can apply to this word, and that will not modify the element of the group. So if one of the following operation is applied, the element of A gamma it represents is not modified. So the first one is pre-reduction. So if ui plus 1 is ur plus or minus 1, then I can cancel the two letters, remove ui plus 1 from w. Okay. It's a new word, but it represents the same element, because I just apply some simple operation. Okay, the second one is the shuffling. if ui and ui plus 1 are given by adjacent vertices, replace ui plus 1 with ui plus 1 ui in W. Okay? So if ui and ui plus 1 are given by two adjacent vertices, I know just from the presentation of the right angle Artin group that the two generators commute. So if I just commute the two letters in the word, it will represent the same element. Right? Okay. So there are there's the obvious operations you can apply to a word without modifying the element of the group it represents. Okay? And the proposition now is that actually it's everything you need. So proposition. So, oh, sorry. Thank you. Oh, sorry, there is another terminology. Okay, so a word that cannot be shortened by applying the moves. Okay, so something I also want to do is to extract some simple representative. Okay, and the idea is that using these operations, I will try to find the shortest possible element, the shortest possible word. Okay, and so if I cannot shorten a word by using this operation, I say that it is graphically reduced or gamma reduced. Okay. So basically the idea is that if it is graphically reduced, then in some sense it is the simplest possible. Okay, so now the proposition is okay, so fix an element in your group, then a word representing G as minimal length. So when I say a word, I always mean with respect to this alphabet. So a word representing G if and only if it is graphically reduced. And moreover, this representative is essentially unique. So if I have two such words, they only differ by finitely many shuffling. Okay. Okay, so this proposition is actually really useful. So let's see a few consequences. So a first consequence is that the word problem is solvable. The reason is that you take a word, okay, you apply the shuffling. It does not modify the length of the word, right? So you can just write down the list of all the possibilities. For all the possibilities, you check whether or not you can apply a reduction. If you can, well, you reduce and you repeat. After just finitely many steps, you have to stop. You have no possible free reduction, and you have two possibilities. Your word is just empty, and your element is trivial, or it's not, and it's not trivial. And that's it. So you can solve the word problem really in a simple way, really. Okay, so the word problem is solvable, but it's not the only consequence. Or maybe one example, maybe. You see that it's not just some weird algorithm that you can apply by using some heavy computer. It's just something you can do by hand on small example. Let's see, your gamma is just a pentagon, A, B, C, D, E. And now the claim is that E, A, D, E minus 1C is equal to B, A, C, B minus 1D. Okay, so how can I verify such inequality? What I can do is I take one word, I try to express it as a graphically reduced word, right? And I find two expressions, and the second part of this proposition tells me that if the two words are equal, then necessarily the two graphically reduced words I obtain must differ only by finitely many shuffling. Right? So just by shifting some letter. Okay, so let's consider this example. E, A, D, E minus 1C. Okay, what I can do is that I can switch E and A, okay, because E and E are adjacent vertices. So okay, so it's just a shuffling. And I obtain A, E, D, E minus 1, C. I can also switch E and D, because E and D are adjacent vertices. This is again the shuffling. And I obtain A, D, E, E minus 1, C. Okay, so now I have a reduction. So it is also equal to ADC. And I cannot simplify further. So ADC is a graphically reduced word. Okay, so now what about the second one? We have BAC B minus 1D. Okay, so I can switch B and A, because B and A are adjacent. So I get A, B, C, B minus 1D. Again, I can switch B and C, because B and C are adjacent. That's fine. This is again a shuffling. And I have A, C, B, B minus 1D. Okay. I have a reduction. B minus 1. I reduce. I get A, C, D. And this is a graphically reduced word. Okay, so now I can compare ADC and ACD. Is it possible to pass from one to another just by applying shufflings? The answer is yes. If I switch C and D, because they are adjacent vertices, I get ADC. Same thing. Okay, so equality. Okay, so another consequence of this proposition is the following, which is important for us, is that for every induced subgraph lambda inside gamma, then the inclusion map, so going from the vertices of lambda to the vertices of gamma, then it induces an injective morphism from A lambda to A gamma. Okay, so by induced, I mean that being adjacent in lambda is the same thing as being adjacent in gamma. So for instance, if I take this graph and if lambda is this subgraph, lambda is not induced, okay, because I have two vertices, they are not adjacent in lambda, but they are adjacent in gamma. Okay? It's not an induced subgraph. Okay. So if you have an induced subgraph in gamma, then actually if you just take the subgroup generated by the generators given by these vertices, it's precisely a right angle arcing groups given by the subgraph. Okay. So it's one sufficient condition to have an embedding. Okay. If one is a subgraph of the other, then it's a subgroup of the other. Okay. So of course, the converse is not true. So just a remark. If you take the right angle arcing group given by three vertices, so this is just a free group of 1, 3. It's a subgroup of F2, which is the right angle arcing group given by two vertices. But of course, this graph is not a subgraph of this graph, just for stupid reason. Right? So the converse is not true even in some very simple example. Yes. Oh, so the proof of this corollary, the proof is just a one-line proof if we have this proposition. So, being lambda reduced is the same thing as being gamma reduced. Forward. Okay, so it's a two-line proof. Forward written over V lambda. So if you take an element of generated by a word given by these generators, then you write it as a gamma reduced word, and if it is non-trivial, it's not empty. But if it is gamma reduced, then it is lambda reduced, and so it's a non-trivial element of a lambda. And conversely, if it is lambda reduced, then it is also gamma reduced, and so it is not trivial. And I didn't say, but the proposition is not really difficult if you know what one component diagrams are. With a short proof of this. And yeah, so I have some details in the notes. Oh, by the way, the notes of the mini course are available on my webpage if you want. So you do not have to take notes if you want. Okay, so this is one other consequence of this proposition. And maybe I can mention a few others. Okay, maybe two. Okay, there are not really difficult consequences here, just observations. So A gamma is free if and only if gamma has no edges, and otherwise you have that z square is a subgroup of a gamma. Okay? So this is essentially obvious if you have this corollary, because if you have an edge, then you take the subgraph, corresponds to the subgraph, which is just an edge, and the corresponding subgroup is just a z square, right? And if you contain the z square, you are not a free group. And the same thing, that A gamma is abelian, is a free abelian. If and only if gamma is complete, and otherwise you contain a non-abelian free subgroup. So same justification. If gamma is not complete, then you can find two non-adjacent vertices, and the subgroup generated is the right-angle Latin group given by just the graph, which is two isolated vertices. It's a free group of rank. Okay. So it sounds obvious, but it's a natural question to ask when you can decide whether or not inside your specific family of groups, whether or not your group is free or whether or not it is abelian. So it's easy consequences, but it's not really obvious in full generality. Really nice that we are able to answer such questions so easily. Okay, maybe an exercise. So deduce that RAAGs are torsion-free. Okay. It's also possible to deduce this consequence from the proposition, but you need maybe a few lines to justify. Okay. Okay, so this is one basic question we can ask, the word problem. The second one is the description of the centralizers. Okay, so but I need two definitions before stating. So definition one. So the join of two graphs say P and C is so So the set of vertices is just a disjoint union of the vertices of the two graphs, and the edges is just you take the edges of the first graph, you take the edges of the second graph, and you take all the edges between the two. Okay, so this is just a complicated way to say that if I take, for instance, two graphs, then the join is just obtained by taking the disjoint union of the two, and I add edges between every vertex for the first one to every vertex to the second one. I add all the possible edges between the two. Right, thank you. Okay, let me try. So, one, two, three. Okay, should be correct. So, a graph that is not a join is irreducible. Okay, so when I say that it's not a join, actually, so what I'm saying is that it's not a join in a non-trivial way. A graph is always a join with the empty graph. Okay, but it's not really interesting. So a graph that is not the join of two non-empty graphs is irreducible. Okay, so this is the first definition. And second one is the following. So a word W U N is cyclically graphically reduced if there do not exist two indices I and j such that the following happens. So first condition, you want so ui is equal to uj minus 1. 2 is that ui can be shuffled to the beginning of the word. Of W, and 3 that uj minus 1 can be shuffled to the end of W. Okay, so basically what I just means is that is just this actually. Yes. Okay, so I think it's rather clear. Yes, but I am supposed to add something. So what it means more or less is that among all the possible graphically reduced words, then I want to isolate some prefix and some suffix, which is just a prefix minus 1. And what is in between is a representative up to conjugacy, which is the shortest possible. And actually, it's my next observation. So every element of A gamma is conjugate to a unique element that can be represented by a cyclically reduced, probably yes. Yeah, I'm just okay, let's say that the word is also graphically reduced. Otherwise, it's not so interesting, actually. Yeah, I will add that. The word is cyclically if it is graphically reduced and if there exists no such. Thank you. Just what? UJ or UJ? Oh, yeah. Or is this one? Yeah. Yeah, yes. So I want that the letters can be shuffled to, yes, to the end. Thank you. I have an explicit example in just a minute. Maybe more. Okay, so every element is conjugate to unique of the group is conjugate to a unique element that can be represented by a cyclically, graphically reduced word. And so definition. And the support, so let's an element G. The support of G is the subgraph of gamma given by the vertices appearing in such a world. Okay, so maybe we should do an example. So X gamma is the following graph. I have a cycle ABCD, A, B, C, D. I have another vertex adjacent to all the vertices, E, and another vertex adjacent to all these vertices, F. Okay, now G is, so it is A minus 2, C, A, B, D, C minus 1, B, A, D. Okay. So it is an element. Now the word is not cyclically graphically reduced because I have A minus 1 and I have A. So A, I can switch A and D because A and D are adjacent. So it's not graphically reduced. So what I want to do is to write A minus 1 times A minus 1, C, A, B, D, C minus 1, B, A, B, sorry, B, D, times A. Okay? So the equality is equality inside the group. Okay? And what I'm saying here is that up to conjugated by A, G can be represented by this word. Now, this word is cyclically graphically reduced. There is no other possibility. And in particular, the support of G, so it's the subgraph of gamma given by the letters in this word. So you have A, B, C, D. So you have this four cycles. So okay. So now from this, I would like to describe the centralizer of an element. So there is the following theorem. Okay, so gamma is a graph, and G is an element of the right angle arting group. Okay, so first step, decompose the support of G as a join. Let's say lambda 1 is lambda k of irreducible subgraphs. Okay, and write G in the following form. So you want H, W1, WK, yes, okay, H minus 1, where Wi is an element of lambda, lambda I. I should write maybe the subgroup generated by the vertices of lambda I. This is for every I. So from such a decomposition, you have a description of the centralizer. So the centralizer of G is, so everything is, you conjugate everything with by H. So you have G1 to GK plus the link of the support H minus, where I will explain everything, where each I is a generator of the maximal cyclic subgroup generated by Wi. Okay, so I need to explain. Yes, so the link is given a subgraph lambda inside gamma, the link of lambda is a subgraph generated by Which one is better?
Right.
Right. Okay. So link of lambda is a subgraph generated by the vertices adjacent to all the vertices of lambda. Okay, so let's look at what it means on this specific example. Okay? So, the maximal subgroup generated by, the maximal subgroup containing Wi. Yes. So in this specific example, so we first look at the support of G. We say that the support of G is just this cycle, A, B, C, D. Okay? Now I want to decompose this support, this subgraph, as a join of irreducible subgraphs. What I can say is that the support of G is the join of AC and BD. Now I write G in this form. So I want to separate the subwords given inside the lambda I. So in this case, in this word, I want to separate the subwords given by AC and BD. So I write G as A minus 1. So I want AC, so I have A minus 1, CA, C minus 1. And now the other letters, B, D square times A. Okay? And I can permute the letters in this way because precisely this is a join. Okay, so this is this representation. Okay, this is this one. Now, I apply just this decomposition. So the centralizer of G, so yeah, you have A minus 1 all the time. So in this case, the question I ask is more or less is this element a power of something? Okay, does it belong to, is the cyclic subgroup generated by this element maximal or not? Which amounts to saying, is this element a power of something? And actually, so it's not. So you have an element, CA, C minus 1, generating your first. So you have, in this case, you have G1 is equal to W1. Okay? But for the second element, you have BD square. So you do not take BD square for G2, you take just BD. So you have plus BD. Okay. And there is this remaining part. So in the graph, you have A, B, C, D, the cycle, and you want to know what is the link of this subgraph. And the link is precisely given by E and F. So E and F are both adjacent to all the vertices inside this cycle. Okay? So in this case, the link is a subgroup. So the subgroup given by the link is a subgroup generated by E and F. And you have your A. Okay. And that's it. This is the description of the centralizer of your element G. And in particular, it is isomorphic to, let's see, you have Z square and you have F2. So F2 is given by the subgroup generated by E and F. So E and F are not adjacent, right? E and F are not adjacent, so they generate a non-abelian free subgroup. And you have the sum of two cyclic groups, so it's a Z square. Okay. So far we have a solution to the word problem and the centralizer problem. And of course there is one very natural problem, is the isomorphism problem. Which is a basic question, but most of the time it's incredibly difficult. So the question is, you take two right-angle arcing groups and you want to determine whether or not the two are isomorphic, right? So in this case, actually the solution is pretty simple. So given two finite graphs say B and C, the groups A phi and A psi are isomorphic if and only if the graphs P and C are isomorphic. So actually, it does not say, it's not saying that the problem, the isomorphism is problem, it is easy. It's saying that the isomorphism problem is as easy as the isomorphic problem in graphs, which is actually quite difficult. But we know that we cannot do better. Because, so it's clear, it should be clear, that if the two graphs are isomorphic, then actually the right angular groups are isomorphic. So we cannot do simpler. So this is, again, this is one this is one of the basic test question was that we know to answer for right angular group. And this is why. In the rest of the mini course, we are focusing on the embedding problem. So the question of, you take two, let's say, finite graphs, and you ask whether or not the two right angular groups, among the two, between the two right angular groups, there exists an embedding. So is one RAAG isomorphic to a subgroup of the other? Okay. And so we already saw one sufficient condition, which is just an embedding of graphs. So an embedding of graphs gives you an embedding of groups. And we also saw that the converse is not true in general. Okay. So, time. So something I would like to say. So maybe I should say something about the references I'm using. So some, it's not really some history, but never mind. Okay, so there is some really important work on the subject, which is due to Kim and Koberda. Yes? Mm-hmm. What do you mean by if you know the presentation? So just abstractly, any kind of presentation? Mm-hmm. Okay, so basically the question amounts to asking if you take a presentation, an arbitrary presentation, you know that it's a right angular group. Is it possible, more or less, to say that, okay, it's a right angular group defined by this particular graph? I would say that it's difficult. It's probably as difficult as the trivial problem. So you get to an arbitrary presentation and you ask, okay, is the group trivial or not? Because it's one particular. The trivial group is a right angular group. Okay? So if this problem is difficult, which it is, so probably this question is more difficult. So I would say that we don't know. Which question? Yes. So for hyperbolic groups, you have the isomorphism problem, which is solved. So in particular, you can ask whether or not your group is trivial. It's a direct consequence of the isomorphism problem. But of course, it's a big theorem. I mean, it's not obvious at all. But yeah, there are a few classes of groups where we know how to solve the isomorphism problem, but usually it's quite difficult. So to prove the theorem, there is some really nice proof that actually does not use groups. It's possible to, what you do is that you associate to the group some algebra. You take, so this is, oh, I just erased the definition, but so the presentation of the group, you take the same thing but for algebras. So you adjust your basis and you say, okay, I want the element of the algebra to commute if they are given by adjacent vertices. And one thing to notice is that if the groups are isomorphic, the algebras are isomorphic. And in the algebras, it's easier to work, and you can prove that if the algebras are isomorphic, then actually the graphs are isomorphic. This is one possible proof. And it's not difficult. I mean, okay, it's not obvious. You need some work, but it's not so difficult. You need a few pages to write all the details. Is it possible to use just this combinatorial framework? I don't know any proof in this direction, but I would say that it's possible, but probably, okay, I don't know. If you like some very combinatorial proofs, probably yes, with a lot of pages of this to distinguish many cases. Yeah, I would say that it's possible, but I would not say that it's enjoyable. But yeah, I would say it's possible. Other question? So some recent progress is due to Guillaume and Coberda from the article, I forgot the title. So embeddability between RAAGs. So it's a very nice, there are some very nice results, and we will discuss these results in lecture number 3, but we will use actually quite different arguments. So Guillaume and Coberda used mapping class groups to prove their results, so which is a rather indirect proof. And the goal of this mini course is to show that it's that we can find a more direct proof and more geometrical proof using this quasi-median geometry that we will see next time. Okay, so this geometry, I will say that refer to one of my papers, so cubicle-like geometry of quasi-median graphs. And applications to geometric group theory. It's a long title, just keep this part. Okay, and the lecture number 4, it will be about some very nice theorem due to Casals-Ruiz. And the title is Embeddability and Universal Theory of Partially Commutative Groups. And so again, the proof, so this is the proof of the fact that in dimension 2 it's possible to solve algorithmically this question. And this is based on Guillaume and Coberda's work. And again, we will show how to prove the same theorem, but using the quasi-median geometry. Okay. Okay, so if you want, there are some the notes on my webpage. Okay, so I have a few minutes left, and I would like to say something about So the mini course only deals with right-angle Artin groups. However, most of the arguments can be applied more or less directly to a more general family of groups, which is called the graph products of groups. So I just would like to define these groups. I just mentioned them at the end of this lecture because, well, they are nice groups. But in the rest of the mini course, I will focus only on right-angle Artin groups, just to simplify the exposition. Okay, so graph products of groups. What you do is that you fix a graph gamma, and you fix a collection of groups indexed by the vertices of the graph. Okay, so now the graph product of groups, gamma G. So this is graph product. So, okay, the short version is we do. So I just write a relative presentation. Okay. So maybe I should expand a little bit. So what I'm saying here is that I'm taking the free product of all the groups in my collection, and I mod out by adding some commutator relations. I say that A and B commutes whenever U and V are adjacent in gamma, and A is inside GU and B is inside GV. So this is just a shorthand. So what I'm saying here is that the group is generated by all the groups from my collection, and I add some commutation. Basically, I want two factors to commute if they are given by two adjacent vertices. And commuting here means that every element of the first group commutes with every element of the second group. So this is the definition of the graph product. So of course we recover right-angle Artin groups. So if GU is infinite cyclic for every U, then the graph product is actually the right-angle Artin group, right? Just by definition. But we can also find some other classical examples. So if GU is Z mod 2 for every U, then gamma G is a so-called right-angled Coxeter group. So right-angled Coxeter group. So similarly, so for right-angle Artin groups, we said that it's an interpolation between free abelian groups and non-abelian free groups. And you have something similar here. So if E gamma, so if you have no edges in your graph, then you have no relations, and your graph product is just a free product. In this case, gamma G is the free product of your groups. And in the opposite direction, if gamma is complete, then gamma G is just the direct sum of all your groups. Okay, this is because you have commutation between any two factors. And so we can say that graph products, in some sense, define an interpolation between free products and direct products. And you have something really similar. So for instance, you have a notion of being graphically reduced. You have exactly the same proposition. You have a description of the centralizers. You have almost exactly the same description. There are some subtleties at some points, but it's more or less the same thing. So for the isomorphism problem, it's more complicated. So in this case, so this is one particular case where the isomorphism problem is not known, so we don't know. In full generality, there are many cases we know, but for arbitrary groups, we don't know. And what I'm going to explain, so what I will explain in the next lectures, about embedding problems, actually all the quasi-median geometry and all the embeddings that we construct, it's possible to do the same thing for graph products. Maybe with some assumptions, but in more general frameworks than just right-angle attributes. Okay, it's possible. So actually, the theorems are not about right-angle attributes, they are really about graph products. So just keep in mind this claim, even though we are working only with right-angle attributes. Okay, and I think that's all for today. Yes, so thank you very much.